We already got a glimpse of how useful Bayesian stats are in the speech and communication sciences. To talk about the frontiers of this field, and as it happens, about best practices to make beautiful plots and pictures, I invited TJ Mahr on the show. A speech pathologist turned data scientist, TJ earned his PhD in communication sciences and disorders in Madison, Wisconsin. On paper, he was studying speech development, word recognition, and word learning in preschoolers, but over the course of his graduate training, he discovered that he really likes programming and working with data. And we'll, of course, talk about that in the show. In short, TJ wrangles data, crunches numbers, plots pictures, and fits models to study how children learn to speak and communicate. On his website, he often writes about Bayesian models, mixed effect models, functional programming in R, or how to plot certain kinds of data. He also got very into the deck building game Slay the Spire this year, and his favorite YouTube channel is a guy who restores paintings. This is Learning Bayesian Statistics, episode 48, recorded June 30, 2021. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.com. That's learnbayesstats.com. Do you want to support the podcast and unlock exclusive Bayesian swag at the same time? Then you can visit my Patreon page at patreon.com/learnbayesstats. Starting at €3, you can get various benefits like the private MBS Slack channel, early access to special episodes, selecting questions for episodes, or even coming on the show. You'll get more details at patreon.com/learnbayesstats. Thanks a lot, folks. I'm very grateful for any support you can bring me.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? Is someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men, dropping placebo-controlled science like I'm Richard Feynman?
TJ Mahr, welcome to Learning Bayesian Statistics.
Thanks for having me.
Yeah, you bet. I'm really happy to have you on the show. I have been following your work for quite a while on Twitter, so quite happy to have you in front of me and not only your Twitter handle. And also that's great to hear from the speech sciences community. We talked about your work a bit in episode 40 with Alison Hilger and Timo Rodger. So yeah, I thought it would be great to have you firsthand and hear about your background, your work, and your different topics, because you work on a lot of different stuff. As usual, though, let's start with your background, because you're mainly into stats now, but it didn't start that way, did it?
No, I was going to be a speech pathologist, i.e. a speech therapist. I was in graduate school for that. I was helping the department with their website, and the chair and my later advisor noticed me and asked if I knew R. And I didn't know R, but I picked it up in her lab, and I found a problem that I was really interested in, which was word recognition. Word recognition from eye tracking data. And it was a very sort of data intensive problem. And so I switched gears and studied word recognition for my PhD. And in order to work on this kind of complicated time series data, I got more and more into statistics, and now I am a statistician.
Again, quite a lot of randomness in your path. I love that. But when you say you're a statistician, by the way, what do you mean? Can you tell listeners how would you define what you're doing nowadays, and also how useful Bayesian statistics are in what you're doing?
Sure. I work as a, data scientist in a research lab for Dr. Catherine Hustad at the University of Wisconsin-Madison. She's been running a longitudinal study of children with cerebral palsy for well over a decade. So children with cerebral palsy is sort of a motor weakness that originates in the brain, so cerebral brain palsy weakness. And it occurs very, very young at birth or within the first 2 years. And so this is a very heterogeneous population that's being tracked longitudinally. And we're running a speech and language battery of tests and tasks on the children, and to track how this population of children develops. And so my job is sort of data wrangling and data crunching and then fitting statistical models. So none of that is about Bayes quite yet. Bayes comes into play as sort of the ideal modeling form. So I can express a lot in a Bayesian model, sort of mixed effects, random effects, like you have longitudinal visits, so you have repeated measures nested in children. And we can explore different subgroups of children by using different modeling features. So it gives me a lot to work with for this really heterogeneous time series data.
That sounds fascinating, by the way. Can't wait to dive into that later in the show.
Okay.
But first, do you remember when you first got introduced to Bayesian stats, and why were they attractive to you? And maybe how often do you use them currently in your work?
Yeah, I've given sort of this spiel a few times of how I got into it and why you should get into it. So this was around 2015, 2016, when psychology was going through its replication crisis. My field, communication sciences and disorders, is sort of really allied with psychology and linguistics. Like if you're going to learn the stats, you're going to take it from the psych department. Just you're doing things, but on special populations, the same kind of things. So we were plugged into that, and a lot of people were just sort of freaked out that there's this large number of studies that did not replicate. And what do? I thought I should level up my stats game. And so the kind of models I was doing were mixed effects models. So I got the Gelman and Hill textbook about multi-level and hierarchical models. And that's a very sneaky book because the first half of it is classical statistics. And then in the middle, they introduce mixed effects, and then they sneak into Bayes. So the back half of the book is all Bayesian. And it was gibberish. It was in JAGs. I didn't understand it. But early on in the book, they talk about confidence intervals, that you can estimate something and put a confidence interval on it. And there's all these sort of formulas you can look up to compute confidence intervals. Or you can just simulate new data and from your model and then report the interval on that. And it was a very sneaky sort of Bayesian posterior predictive check. But it was very liberating to see the idea that I don't need to memorize these equations. I can just have the model produce new data and then just use data analysis on that large sample of simulations or posterior draws. So that's sort of the first appeal of it, was that it plugs into just sort of data analysis tools that you get to do all these statistical inferences, but you're just like summarizing and taking the interval of data. Now, there's another thing that I read at this time, which was called a slide deck called Statistics for Hackers. And it had the idea that if you can write a for loop, you can do statistics. It does the same sort of approach where you don't need to memorize these analytical formulas. You can just do your data analysis stuff. So you tell if there's a difference between two groups. Well, you could just randomly swap the labels and see how it matches the data, and you've done a permutation test. You do that like 1,000 times, and you just report sort of a summary statistic and how it compares with the observed. Bootstrap is something similar where you resample your data and you compute the statistic. And so Bayes is just sort of Bayes on posterior samples. It's the next version of that. And it's just really powerful that what you need are, after you fit the model and get the samples, what you need are just basic data wrangling skills. And you can quantify your uncertainty about anything produced from the model. That was the other ingredient in the air, was sort of it's easier if you know data reduction, data analysis stuff. And then the final element in the air at this time was that Statistical Rethinking's first edition came out, and Richard Mickelreath put all of his stuff online. And then the BRMS and R-STAN-ARM packages came out at the same time in early 2016. And so it was just like the best time to take on Bayesian statistics. Best time besides now.
Yeah, this is definitely a good time to take up Bayesian statistics. You're right. I'm guessing it's definitely easier to do that now or 5 years ago, as you said, than in the 1990s with, all the awesome resources we have at our disposal now. And so, yeah, from what you're saying, as a lot of people, you seem to have been drawn to Bayesian statistics through a very pragmatic approach, right? That you had a problem and you discovered that Bayesian stats could help you solve that problem.
It helped me solve the problem. I could fit classical models and do a little more legwork and get similar things. But there's sort of a understandability where I know what I'm doing much more when I'm doing the Bayesian model, because there's like 3 ingredients: your priors, your likelihood, and your data. And so everything just sort of runs and you get the posterior samples and then you work on them. And it's a very simple framework that pulls a lot in. And so it was pragmatic in that it helps me tackle my problems. I can fit like practically anything in VRMS, but I have a good sense of what's going on and what it's doing at sort of, what the model's doing.
Yeah. Did that occur to you from the beginning, or like was it more the idea of confidence intervals that are super simple in the Bayesian framework, both to compute and to interpret, especially? Was that the main ingredient? And then you discovered that you had a lot of control over your models, that you had to explicit your assumptions and so on. Was that from the beginning, or did you discover that a bit later, once you already had modeled a few Bayesian models?
Yeah, so I think that you don't really have a good grasp on the concepts until later on and you play with the models. The really empowering thing early on is that the posterior is such an easy thing to work with, provided that you have good data wrangling skills. The Gelman and Hill book had this model where it was predicting income from height, and this do people who are taller get paid more, and there were these other predictors. But then they log scaled the income and log scaled something else and talked about how hard it would be to get a really nice estimate of your uncertainty about what the effect is. But they just simulated new data from the implied posterior, and they had a really nice crisp, I guess not crisp, they really had a nice uncertainty interval afterwards. And that sort of highlighted to me that you can answer a lot more questions more easily with this approach. And that's what made it appealing.
I see.
But they're easier to work with once you get past the fact that you have 10,000 samples.
Yeah, okay. I completely see what you mean. And I have to say I had kind of the same experience. Actually, that's really how I got back into Bayesian statistics, was really through the confidence intervals that are so intuitive to interpret. And when you have a use case where uncertainty is very important to you and uncertainty estimation is really core to your analysis, then often you turn to Bayesian stats and methods. As you said, I like to ask this question, but I think you already answered. But basically, when you work on a Bayesian model, you mainly use R and BRMS, right?
Yeah, R and BRMS. BRMS is simply amazing. It stands on the shoulders of giants. R has this really nice formula syntax for fitting a regression model. And then LME4, a linear mixed effects package, sort of expanded that to create a syntax for random effects and repeated measures. And then BRMS took that and then added a few more things. And so now you can express all kinds of models built on this sort of syntax that you're used to if you use R.
Yeah, I see what you mean. And just to make clear to listeners, when you're talking about mixed effects models. You're talking about like what also people call random effects models or hierarchical models, etc. Right?
Yeah, that's my generic term for it.
Yeah. Just want to make sure that we are indeed talking about the same thing. That's always best. Okay, and actually now I'd like to talk more about what you do. Okay, we talked about the fact that you're more into the methods now, that you use a lot of Bayesian statistics, but you're still mainly working in the speech sciences field. So can you tell us how Bayesian methods are used in the speech sciences? And maybe if you want, you can take as an example research paper or experiment that is one of your favorite on this topic.
But right now, Bayesian methods are used seldomly or sparingly in our field, in that they kind of have to advertise themselves as a novel approach to a modeling problem in I would say, the clinical speech sciences field. So how do they help us? Well, when we have longitudinal data, we have repeated measurements. When we have experiments, like a speech perception experiment, we have items nested in speakers and trials nested inside of words. So you're going to want to model the variance of the speakers and model the variance of the items. So it's your standard hierarchical mixed effects arrangement. So they help there. You can do this with classical models, but you can kind of do more fun and interesting things with the Bayesian model, like simulate what a new child or speaker or item would do from the data set. So it's sort of drawing from the posterior predictive distribution. And I recently published a paper about the development of intelligibility in children with cerebral palsy. So intelligibility is what percentage of words that a naive listener can understand when you speak. These children, a lot of them have speech motor deficits, so that speech comes out slurred or otherwise difficult for listeners to hear. So we wanted to measure how difficult or how intelligible are they to listeners, and then how does that change over time in this population and in different subgroups within this population. And one thing about working in the child language development field is that you have a lot of prior knowledge, because children start out as babies that don't talk, and then they end as adults that do talk, and they talk very well. So there's this sort of floor and ceiling. And so we modeled this using a logistic growth curve that starts at 0 and ends at 100%. And so then it became a nonlinear mixed effects model where you have this logistic curve. And so this is like BRMS made this really, really simple, because instead of like inferring the shape of the curve from the data, you specify the shape beforehand, and then you try to find the best curve features to fit the data. And so there's like those parameters include the final height, asymptote, the cross point where the growth is the steepest, things like that. And so Bayes let me fit a nonlinear mixed effects beta regression model. It's just really simple in BRMS once I got it running. There were a few problems, like you need to have decent priors to get it going, but in the end, it was great. And as part of the application of the paper, I sampled from the posterior predictive distribution to show that, suppose you had a data point from one child at age 4. That's all you know about this child. Based on the model and the children that the model has seen, what outcomes and trajectories are plausible. So now you have a forecasting thing that you get with Bayes. And so that was a really cool application of Bayes in the field.
Yeah, that sounds quite fascinating. Actually, can you talk a bit about the problems you had with the priors? I think it will resonate with listeners and probably help a bunch of others.
Okay, so you're on the beta, you're doing a beta regression. So everything is between 0 and 1. Your data comes in as proportions. If you try doing like a normal Gaussian model, you would find like values that shoot off above 100%. And so you have to, you get the outcome family right.
Yeah.
And then the model uses the Logit scale internally so that it's the log odds, so that 50% intelligibility is 0 logits. Now, a logit change of 1 is like a change from 50% to 78%. And so like your default prior of a normal with 0, 5, when you sampled from that prior predictive distribution, you had children you simulate plausible data from the model from the priors. You had lines that went straight up because the prior scale was too large, and it implied lines where a child grew 100% in a single month. So you had to tune the model in order to come up with, like, really shrink down the prior to a narrow range so that you wouldn't get lines that went straight up. The other thing was the random effect variances, where you would implied, like, you get these really widespread of plausible child means within a group. And so you'd have a clump piled at 100% and a clump piled at 0% because like 3, 4, and 5 on the logit scale are both at 99.9. And so you get things piled up in the tails of the proportion scale. So you also had to rein those in. The way that I worked through this was simulating plausible trajectories from the priors, like stuff that doesn't show a complete childhood development in the course of a month. Stuff that doesn't have all the growth taking place before age 2. Children learn to talk after age 2. So you set a prior on the age of steepest growth around age 4 plus or minus 2 years. So that's pulling in domain knowledge. Just like we know how kids talk. We know when it changes. So we're going to incorporate that right into the priors. And then we're going to calibrate the priors by simulating plausible trajectories.
Yeah, that makes that resonates at least with my experience too, because I do work a lot with count data, which means when you're using regression, you need a link function. That's what you talked about, that the log odds are also called the logistic function. And of course, this distorts the parameter space, which is on the real line, and it distorts it into the 0-1 space so that it becomes a probability. And of course, that's not linear. So if you're using classic normal 0-10 prior, for instance, you get very, very implausible prior predictive samples, because you get usually very extreme behavior on your prior predictive samples compared to what you would expect from reality. And that's not only scientifically problematic, it's also a problem for the sampler, right? I'm guessing that you had some of these problems when you started using priors that were too wide. And I mean, that's an interesting question. How did you notice that the problem was coming from your priors and that you needed to get into that a bit more?
In this particular example, in BRMS, so when you're fitting this sort of nonlinear model, in the classical packages, you probably have to provide a starting value so that it can work from there for its optimization problem. And in BRMS, you have to provide a prior. It has no default priors for these nonlinear models. And so you have to give it something to start with. And then the sampler then complains about divergences or other issues. And so then you tune the priors and you look at the prior predictive stuff. Yeah, so you rely a lot on stans. I use stan. That's what BRMS is built on. You rely a lot on its complaints, because if it's going slow, that's usually a symptom that there's something wrong with your model. I remember once I fit a stan model by hand, a polynomial model with a cubic term, a quadratic term, and a linear term, and it took 6 hours. Oh. And that's because I had a typo where I wrote the number 2 in place of the number 3, so it had 2 quadratic terms. And they were just like knocking each other out on each sample, and it took forever. And so like the model went slow because I wrote a bad model. Like the model wants to run fast. So that's like the Folk theorem of statistical computing in the Gelman verse, where if your sampler or software is having problems, there's something wrong with your model. So that's a good heuristic in Bayes.
Yeah, definitely. And I love that Yeah, I love that you're saying that actually it's a good thing to have all these warnings and divergencies and stuff like that. Because when you see them, you're quite happy because it tells you how to improve your model. And here really, your model had a problem. HMC cried out loud, and that made you understand that, oh, okay, actually there is an unidentifiability in there. I should go and fix that. This is really invaluable, actually.
And those, they help, because when HMC, Hamiltonian Monte Carlo, cries out, as you said, it's having troubles, but they're not sufficient. They don't tell you that you have a good model in the end. Like, you could have given it super strong priors and it just sits in one place and ignores the data.
Yeah, definitely. It's a necessary but not sufficient condition. Like you want to have no warnings and no divergencies and good R-hats, etc. But that can't tell you that your model doesn't make scientific sense, for instance. That's more the creative part and the research part, but not the computing part or the statistical workflow. That's super interesting. So yeah, can you tell us, still talking about the speech sciences field, what are the current main challenges in the field, like the frontiers of research?
That is a difficult question to answer because you can go a few different ways with it. Like, you could take the clinical approach, like what are the main clinical problems, or if I'm more the statistician, what are the main statistical problems?
I'd say pick your favorite.
There's always new kinds of data coming in, and that the field has to learn how to wrangle with those data and adapt to them. So maybe a decade ago, or maybe two, and I'm speaking kind of ignorantly about this, like MRI data was sort of something that had to be wrangled with and you learned how to work with. And in sort of child language research, we now record children's speech for a whole entire day. We put a recorder on them and we record everything around them. And so now you have this massive 16-hour audio corpus for a single day for a single child. So this is an entirely new kind of data, which is massive audio recording. How do you even segment that into meaningful units? During COVID, when we couldn't do experiments in person, we started doing listening experiments online. So that's sort of, it's not an entirely new kind of data, but sort of the field is going to have an influx of online listener experiments that have to be wrangled with. And you have to deal with the variability that results from an online population, not a community recruited population. So I feel like the challenges are that, there's always new kinds of data which are related to new kinds of problems. That's not even getting into sort of telehealth things where you're doing speech and language testing remotely via an app, even creating that app, things like that. So it's sort of technology is getting bigger and bigger and richer, and how do we use that to generate insights?
Yeah, and are those topics that you are currently working on?
We recently started some online listener experiments, so that'll be something to play with, and we have piloted some day-long audio recording stuff, so that's something we'll be working on. Gave those examples because they are close at hand in my experience.
Yeah.
Would you be surprised that I am working on the frontiers of the science, in my opinion? Like,
yeah, well, that's not that surprising. I mean, that's what you usually do in academia, I guess. Otherwise, it's less interesting, maybe. Yeah, but definitely once that research is out, please tell us. I guess that would be very interesting. Maybe a larger question is, then how Bayesian is your field right now? Because you're using these kind of methods, but are you rather in the minority or are you starting to be in the majority of papers?
Definitely in the minority. And again, I don't think it matters in a lot of problems where you run an experiment and you collect two samples and you want to know, does this manipulation do anything? Like the classical model is fine. For a lot of these sort of simpler experimental designs, right? So there's no reason to fit the Bayesian model to that unless you're going to leverage prior information in an interesting way, do some cool posterior predictive stuff, or maybe integrate different kinds of information together. Or unless, I guess, you have a full generative model that you want to see how well that fits with the data. So the field is not super Bayesian, but me and people like Alison Hilger, like we're not trendsetters and we're not outliers. This is the tool we used for our problems and it worked really well for us. The majority of the papers that I've worked on, maybe half, use classical methods. So it's not that like I am crusading for the Bayesian cause, but the best tool for one particular paper was a generalized additive model with location, shape, and scale, aka a GAMLess, because we were doing developmental growth curves, and that approach was well recommended. Like we didn't need to do anything particularly complicated that required Bayes, and if I had my druthers, it would have been fully Bayesian, but we stuck with GAMLess because it was good enough, and it was novel in its own right with respect to the field. I want to say pick your battles, because it's not really a battle. I haven't had anyone push back against Bayes when I've written a paper. They just they want more explanation and guidance through it. So there's sort of this teaching overhead you do whenever you use it now for the time being. And so we are a minority in the field, but we do cool and interesting things with it, and people have been really receptive to it.
I guess that's super encouraging. It's great to hear that, actually, that you don't have any particular problems when submitting papers, or else you just need to walk people a bit through it and through why you're using these methods, which in a way is kind of expected because, well, most people don't have these kind of classes when they do a classic statistics curriculum. That may be unfortunate by some aspects, but once that's done, it's expected that you have to walk people through that a bit more. But in the end, as you say, that's not been a big issue for you in the field. And that's awesome, because in the end, that means that you folks can use the best method available for the problem at hand, which is in the end all that matters. That's a good roundup of what you're doing in the speech sciences. But I know you also love functional programming. And I have to say, I was surprised to learn that, because that's not a topic that I'm used to seeing emphasized in academia. It's definitely emphasized in open source development, but I've not seen a lot of emphasis on that in academia, at least in what I've seen, which is biased sample, of course. But I'm curious then, can you tell us what you love about it and how it helps?
Sure, I'm really enthusiastic about functional programming, but with apologies to Will Kurt and like his Haskell flavor of functional programming, I mean something more like R and JavaScript or Scheme, where you can build up a language for a problem really quickly by creating functions and then have functions work on other functions. And so you start really simple and build up this whole sort of meta language in order to work on a particular problem. And it all goes back, at least for me and my understanding, is that it goes back to a textbook called The Structure and Interpretation of Computer Programs, which was the MIT textbook. And it uses a language called Scheme, which is a Lisp-like language, but you can pass around functions that return other functions, and you do all this cool stuff. And you can manipulate how the language works and how it evaluates things. But the cover of that book is like a wizard. It's two wizards, and there's like this big lambda symbol, like they're casting magic spells. And so when I think of functional programming, I think of creating magic spells, just whipping things together, and you feel just unstoppable. And so I'm really enthusiastic about that sense of functional programming.
Yeah, I see what you mean. Really, that's definitely something that's emphasized in a Python ecosystem too. And yeah, really agree with you that that makes everything first more easy to maintain, not necessarily easier to understand. That's something I noticed recently, that it's awesome to have your package wrapped in classes and functions and so on. That's so much easier to use and to maintain. But to understand it, like if you want to call that function or that class and so on, then that's more intricate than just having a script that you can run in a Jupyter notebook. I find that if I want to understand really how a package works or a model works, I really love having just the bare minimum code necessary to run it and see what goes where and what changes when I change something, which is not something you can easily do when you're working with classes and functions. So I guess it's something for more mature implementations, but that's definitely something you should strive for, and that makes life easier for both users and maintainers.
That's sort of the pros and cons of abstraction. That abstraction lets you hide details, but then when you read the code, it's less clear what's going on because everything becomes more generic.
Yeah, that's definitely something I've experienced recently. So yeah, just something to be aware of. And so I'm curious then how, because you also, and I guess that's linked, you also are very enthusiastic about reproducible computing. And I mean, this is clearly linked to functional programming. But then I'm curious what are you doing in your own work and your own field to make those topics more of importance and something that should be in all the minds instead of being something you just think about at the very end, if at all?
Yeah, I'm enthusiastic about reproducibility too. You don't want to be in that situation where you write up a bunch of modeling results and then you find out later that one participant who should have been excluded because of some screening thing needs to be excluded, and then everything needs to be updated manually. You want to generate those results on the fly whenever the data changes as needed. And so in R, we have a couple of tools that make this much easier. So like in knitr/R Markdown, you write in Markdown and you can insert chunks of R code or R expressions that are evaluated and then included in the final document. So this document is created like on the fly so that if the data set that's being read in changes, everything in this document updates and it works. So that's sort of the first affordance we have in R for reproducibility. And then there's this whole other burgeoning ecosystem for a package called targets, which is something like make as a tool, a very old tool for compiling programs, and it will do things whenever. It's a workflow manager that'll run tasks whenever dependencies change. So it's a dependency manager. And targets is a tool like that for R. So you can read in files and then it hashes them so that it knows whether the file's changed. And then it'll run downstream steps. And so you have this sort of graphical database connecting data to models to files, and everything will be regenerated if anything has changed, so that you have a fully reproducible set of results. And at the very end of a project, if I'm feeling worried, I'll just wipe out everything in the cache and then rebuild it all from scratch and then check and get whether any of the output has changed. And it's such a cool feeling that I wrote up this whole analysis and all these figures and nothing changed when I ran the code twice. And so I'm enthusiastic about knitr, R, and targets, and I try to advertise them. I guess that's what I'm doing to support reproducibility in the field. The other thing that I do occasionally is I'll write a tutorial in the supplemental materials sort of showing the code that was used to generate each of the main inferences. So that logistic growth curve paper is sort of a mini tutorial on BRMS where I start sort of adding piece by piece to the formula until I get to the final model. And so that's kind of reproducibility because it shows the code that I used, but it's also just sort of documenting methods. So reproducibility is also documentation because nothing was manually written down or transferred or saved. It's all just what you see what you have is what you get in the end.
I mean, that tool sounds super interesting. Can you put that in the show notes maybe for listeners? Because I'm guessing that people will be interested in that. That sounds great.
Yeah, it's I guess its first public releases at the beginning of the year. There's a whole book for it online. Yeah, I'll include that.
Yeah, definitely. That sounds really interesting. Awesome. And you don't only love functional programming or reproducible computing, you also love plots and pictures, I heard. So do you have best practices for us about communicating the results of our Bayesian models? And I guess it's also very interesting to hear from you on this topic because, as you say, you're in a field that's not mainly Bayesian. So I'm also curious, how you make your plots and pictures so that the whole audience and the whole field can understand what you'll put in your paper.
Sure. So when I give a presentation and I have to describe my model, I have to do it visually and quickly. And so I have to come up with some really interesting and informative pictures for those models to quickly instill what's going on. So then when I do that, I write a blog post, usually to show it off. So one example I have is called Bayes' theorem in 3 panels. Right? Bayes' theorem is the posterior is proportional to the prior times the likelihood. We're just ignoring the denominator for now. So the first panel draws from the prior predictive distribution. So all the regression lines that are plausible before seeing the data. Just this big pile of lines. And then the middle panel is how well do the lines fit the data? And so there you showed your maximum likelihood estimate line alongside the points that are the observed data. And then the final one, you show all the lines that are plausible after seeing the data. So you don't even use the words prior likelihood or posterior. You say plausible before, what fits, and then what's plausible after. And then the third panel is the points with sort of a spaghetti plot of regression lines. And so visually, to quickly teach Bayes like that, you visually have to use something like that instead of the equation. So that's sort of this form of communication that is educating the audience very quickly about it. The other technique is a lot of annotations. So I have another example where I describe the logistic line and then I annotate each part of it where there's the steepest point and asymptote, and I color those to match parts of a colored equation. So that's sort of labeling and annotation. You can't have too much of it. Maybe you can. So my other example I have is sort of trying to distill the intuition behind a mixed effects model really quickly. So I have a series of panels that are just the observed data, 1 panel per child. And then the middle panel is sort of the inferred population. And it's sort of all these bands, this heat map of which trajectories are plausible. And then the bottom panels are sort of, then each child from the top row has a regression line. It's weird describing plots auditorily.
That's the challenge. I've not been kind to you there.
You sort of you take the sequence of steps of data, model, predictions, and you visually encode them in sort of, left to right or bottom to top. And you can sort of see what you start with data, and then you get model, and then you get predictions. So that's sort of my flavor of visualizations that I do a lot. I also contribute to the Bayes plot package, which is, I would say, diagnostic plotting for Bayesian models. So you give it a stand model, and it shows the posterior predictive density curves. So you have a dark blue line for the observed data's density, and then 50 light blue lines that are densities for the posterior predictive. So data that, if the model simulated new data, these would be the densities. And you can very quickly see the mismatch between what you have and what data your model thinks is plausible. So another way, a point of sort of model communication is sort of highlighting what you have in hand and then showing all the sort of a sample from the posterior of a spaghetti plot or density curve.
And well done on your work on base plot. I know that in the RVs team, where we have the same goal, like the goal of the package is very similar to base plots. And so, yeah, we definitely love what you guys are doing there. So thanks and well done on that.
I occasionally contribute. I think the most recent thing I did were the trace rank plots, so a couple years ago, a lot of STAN people were rethinking RHAT and what RHAT does and came up with other diagnostics. And so one of them was looking at the rankings of values from each chain in the posterior. So if one of your 4 chains dominates the top 10% of values in terms of ranks, then that chain is working in a different bit of the parameter space than the rest of the chains. And so I created, this was inspired by a plot by Richard McElreath, but I created something that would sort of show the rank sort of it's like a trace plot where you have lines overlapping, but it's the rankings from each chain. And I'm doing hand gestures that don't help the audience right now. I also want to give a shout out for Bayesian plotting to the ggdist package and tidybayes package, which create new primitives for plotting. So we're familiar with sort of your distribution curve or maybe your box plot, but this creates other shapes that are used to express sort of essential tendency and range. So a half an eye shape or an eye shape, or representing a posterior as a series of stacked dots so that there's only 100 dots, so that you can quickly eyeball those 5 dots are 5% of the posterior.
Yeah, I love those too. Can you put some links to those blog posts in the show notes? You were saying that you often write blog posts when you're doing new plots or pictures also. I think it would be great to have references to those in the show notes because, as you say, I think you did a great job there, but describing plots on a podcast is always hard. So let's give people the opportunity to go in and dive into those. Okay, a question I like to ask from time to time, because also my goal with this podcast is to demystify mistakes, if you want, on that, and to convey the message that you don't have to be perfect to do Bayesian models, and that actually everybody makes mistakes, and the goal is not to not make those, but maybe quite the contrary, actually. That's how you learn. So I'm wondering if you have in mind a modeling mistake that you did one day, and how did you end up realizing it and solving it?
Earlier, I mentioned that one time I made Stan run forever because I mistyped a 2 for a 3. And so Stan was really good at telling me that I messed up because it took forever to run. And so the Stan's not brittleness, its fussiness is a good way to catch a lot of mistakes because it'll just stop and then all of a sudden I have to diagnose what's going on. There's a whole class of mistakes that I don't even remember because Stan caught them for me because it started running forever, right? Before Stan, a classical model, that's going to run fast because it's not going to sample the posterior and it's going to give you a result and you're not really going to have a sense of anything going wrong. And I think there's one example I can think of, which was subtle at the time, where I was computing the log odds for 2 events. So this was one of those eye tracking experiments where there are 2 images on the screen and there's a baby sitting on a parent's lap and they hear something like find the dog. And then there's a dog and a cat on the screen. And we want to see how quickly they can look to the word dog when they hear it. Do they need to hear all the word dog? What's their reaction time? Are they able to do this reliably? So this is a eye tracking word recognition experiment. And I was computing the log odds of looks to the target versus the distractor. But if you were doing this on a trial by trial, frame by frame basis, a child blinks or fusses out, you have a lot of missing data. And so I was treating those missing data as not as NAs and not as, at first I tried zeros, right? They had 1 look to the target and 0 to the distractor. But 1 divided by 0 is infinity, and so the model complained. And so I did 1 divided by 0.0001, which is just a very small number that's supposed to be like 0. Well, when you sort of work out that fraction, that means that they had, what is that, like 1,000 looks to the target and 1 look to the distractor. You're actually saying something much different than 1 versus 0 or 1 versus missing. You're saying a very large, precise number. And so this was very early on for me, but it was sort of a subtle mistake where I thought I was doing an appropriate continuity correction, but actually I was feeding it a lot of information so that it was making very overconfident and overestimated effects. Yeah, and I think I just had the model take care of it. Like I told it the 2 columns to look at, and it sorted it out from there. Like other people have done this, have sorted this out. They know what to do.
Yeah, they do. So, I mean, that's great that you had that as a resource then, I guess. But how did you feel when you discovered that mistake? What went into your head?
It was weird. Like, what's going on here? Why is it predicting 100% accuracy? It shouldn't be. Like, why is everything going off the rails? And then you kind of roll back the code, and it's this early data preparation step that seemed innocuous and that actually prevented other errors. And so it was a relief to figure out that that was the problem. It was a relief to find that it was isolated. But then it was frustrated that I didn't know how to solve this problem because I didn't know what to Google.
Yeah.
I'm going to look up logistic regression, missing data. No, this isn't right. And then the phrase that seemed to help was continuity correction, and what to do when you have, for a logistic regression model, continuity correct. Like that seemed to put me on the right track and connect me to a literature that helped me understand the problem, what was going on. And so that's it's a relief to have it identified, but then you have a whole set of other frustrations because you're trying to describe what this problem is and you don't know the lingo quite yet.
Yeah, I mean, that's definitely challenging, but that's the life of a statistician, right? Even very experienced ones. Okay, before time is flying by, and so before we close up the show, I'm wondering if there is like a method or a type of models that you particularly like and would like to share with us.
This last year, I've been really into generalized additive models, and I wrote, I think, like my magnum opus of a blog post, which is unpacking how generalized additive models that are fitting smoothing splines are the same thing as random effects. Like I had heard people make this connection before, and on both sides, like people who do mixed effects, drawing out the relationship that partial pooling that is done by a mixed model is kind of like smoothing that is done by a spline model. And so I went deep trying to unpack, where does this connection occur? Can you really use a random effects hierarchical model to fit a smoothing spline? That doesn't quite make sense. I worked through this whole set of examples, and it's really neat because it drew a connection in my head between what's going on in partial pooling and smoothing splines. So just to unpack a little, in the generalized additive model, you're going to fit some nonlinear shape of the data. So the curve can wiggle up and down and follow the data. But you want to penalize it so that it doesn't overfit the data. And so it tries to penalize its wiggliness. And so you have this set of sort of basic functions that are spline. So you have this set of like 10 little wiggly bumps, and they add together to approximate a nonlinear curve. So you have 10 predictors that are related, and you want to penalize them so that they don't overfit the data. And then the mirror case is happening in a mixed effects model. Sort of an analogous thing is happening where we have like maybe 10 groups, and we don't want to overfit the data. We want them to share information with each other. So we're going to partially pool information so that it in the end acts as a penalty or a smoother, so that instead of having really jagged predictions for each group, we kind of smooth them out and learn from the other groups. And so random intercept models are actually smoothers. And there's this really neat thing to think about, that they are smoothing categories together. Simon Wood has this He's the one who wrote the MGCV package in the main textbook, fitting generalized additive models. But he has like this throwaway line that we use smoothing to use random effects because we think that nature is more smooth than jagged or wiggly. And I think that's a really cool thing that we're doing when we do Bayes with the hierarchical model, is that we're allowing things to learn from each other and be smoother, because our prior is that things are more likely to be sort of smoothed than jagged and spiky.
Interesting. And you have a blog post about that, you were saying?
Yes.
Nice.
Yes.
We definitely need to add that in the show notes for our listeners. That sounds really interesting.
It goes deep because I show that the exact same stand code is used to fit the random intercept model in BRMS and the smoothing spline model in BRMS. Like, they are using the exact same lines of stand code. And so your mixed effect partial pooling is smoothing. It's really cool. You just draw together these two fields with stand code.
Yeah, super cool. Yeah, definitely please add that to the show notes. That's going to be very fun to read. Okay, maybe last question before the last two questions. And maybe you talk about that in the blog post, but what are the most challenging parts when you work with those kinds of models that you just described? So they're either the splines or the mixed effect models. But I guess the mixed effect models, we already talked about that. So maybe talk about the splines.
Using splines in Bayes is kind of a trickier arrangement because you can get all sorts of nonlinear shapes, because it can do whatever it needs to follow the data and constrain its wiggliness. So then your prior predictive workflow is sort of more complicated because, well, it shouldn't do that. That one shouldn't do that. Like, what do you do? And so I don't think I have adequate practice yet, like giving solid advice on how to work through the priors and that stuff for this problem. It's just sort of, when you start getting into this, I guess, semi-parametric or non-parametric stuff, like, it's harder to diagnose and unpack what's going on behind the scenes. So that's the challenge, is that you're on the frontier of like your understanding.
Yeah, that's also the impression I have not used splines enough yet to my taste, but that's the intuition I had to. Awesome. Well, TJ, I think it's gonna time to call it a show. But before letting you go, as usual, I'm gonna ask you the two questions I ask every guest at the end of the show. First one, if you had unlimited time and resources, which problem would you try to solve?
I had unlimited resources. I feel like the problem that everyone should be solving then is climate change. Like, do something about it, do anything about it. Like, if I had unlimited resources and all the time in the world, I guess I would have to work on that, because that's how you save the world.
Yeah, that's a popular answer in the show. So that's great that you are now joining this team. I guess we are close to solving it then.
An additive model.
Yeah, exactly.
We'll have a spline so that the temperature can wiggle back down.
Yeah, that's perfect. Yeah. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Thought about this for a bit, and I think Douglas Hofstadter. He wrote a famous book called Gödel-Escher-Bach, which draws the connection between Gödel's incompleteness theorems, Bach's music, and Escher's sort of self-referential drawings. And it sort of plays with the paradoxes of self-reference and sort of the beauty of self-reference. And it has like these dialogues that are actually anagrams, where it is the same lines in the first half, just in reverse order in the second half. And it goes deep on sort of philosophical troubles about information and what is information and what is the self. It's just like really fun and beautiful scientific mathematical thinking. But it's also like, it's fun and playful. But he also seems like a very kind thinker in his prose. And so it just seems like I have so much to learn from you. Like a Richard Mickelreath type, just so much wisdom in this scientific writing.
Yeah, Yeah, nice choice. I feel like I want to be in this dinner too. Okay, thanks a lot, TJ. I really learned a lot again about speech sciences, and really this is a fascinating field, both because you work on intellectually interesting topics, but also you have kind of challenging models that can feed your statistical curiosity. So I mean, it's really a very interesting field. So thanks a lot for diving into all that with us and working through all of that and what you do and what you love doing. As usual, I put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, TJ, for taking the time and being on this show.
Thank you for having me. This was a lot of fun.
You bet. Come back anytime. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.